The purpose of the issue paper that I'm summarizing today is to provide background detailing the underlying complexities and challenges faced by U.S. agriculture to sustainably meet water quality nutrient reduction goals while advancing productivity. I'd like to begin by recognizing the all-star task force team of research engineers, soil scientists, economists, and agronomists. It was a great team to work with to pull all this information together and really come up with a comprehensive review of agricultural water quality issues. As the world's population is projected to grow by 2 billion people over the next 30 years, sustainable nutrient management will be critical for global food and water security. To meet the demands of this growing population, the world will need to produce 25 to 70% more food, fiber, and feed. Although grain yield has been increasing linearly, the relative rate of increase is actually decreasing, and it's currently at a point below the rate needed to guard against negative consequences. One of the primary reasons why we have been seeing an increase in grain yield with time is because of the use of fertilizers. With fertilizers, we can produce more grain on fewer acres. Readily available organic nutrient sources alone cannot maintain current crop production levels. Looking at studies that have been conducted in the United States, fertilizer has attributed on average between 40 to 60% of the yield. However, we're often reminded as we open up the newspaper in the morning or turn on the radio of the negative consequences of agricultural nutrients on our environment. So what are the controls on nutrient loss? The balance that we're faced with today is meeting these production goals while reducing the environmental impact. Specifically for our discussion today, that's going to be the impact on water quality. Let's take a look at what can happen to nutrients when they are applied. 4 main processes are prevalent in soil nutrient cycling. Addition is the input of nutrients to the soil system. Translocation is the movement of nutrients within the soil without changing form. Transformation is the chemical or biological conversion between forms of an element. Loss, this is the movement of nutrients out of the soil system through the harvested grain with water or to the atmosphere as gas. To reduce loss, we can start by focusing at the nutrient source. One approach is to estimate nutrient use efficiency. Crop harvest removes nutrients from the field, which farmers then replace through the use of biosolids, manure, or fertilizer application. This is partial because this calculates one moment in time. So for example, if you're quantifying for a year. And it doesn't quantify the losses of the nutrients or the transformation. Nutrient use efficiency greater than 1 represents a scenario where crops are mining nutrients from the soil. So what's being taken up by the crop and harvested off the field is greater than what's actually being applied that year by the fertilizer or the manure. When the nutrient use efficiency is less than 1, there could be nutrient storage in the soil. And this is what typically is reviewed for potential losses into the environmental system. To increase nutrient use efficiency and reduce the risk for losses, the fertilizer industry has led the 4R Nutrient Stewardship Initiative, which promotes using the right source of fertilizer at the right rate for crop needs, at the right time to match crop uptake, and in the right place so that it can be efficiently utilized by the crops. Sometimes even when nutrient use efficiency is high, there can still be nutrient losses. So for example, even in native landscapes like forest systems or prairies. To understand how this happens, let's take a look at the hydrologic cycle. The magnitude of nutrient concentrations in runoff or leachate from recently applied sources is generally a factor of the rate, the form, and the solubility of the source, as well as the dominant hydrologic transport mechanism. When a raindrop hits the ground, it can infiltrate the soil and make its way into drain tiles, or it can continue seeping deep into the groundwater system. Water that infiltrates can cycle back into the surface water, and depending on the geology, it takes all different rates for this to happen. It can be just a couple of days to over 50 years. And I point that out because we often talk about water as either surface water or groundwater, but really they're connected. And we can't forget that when we're talking about nutrient transport. Now, if the precipitation is falling at a rate faster than what it can infiltrate, then that's when we may end up with surface runoff. The water that does not infiltrate or run off the surface can be transpired by plants or evaporated into the atmosphere. If we add the nitrogen cycle onto the figure of the hydrologic cycle, we can see the pathways for loss. Soil has a negative charge, so nitrate with a negative charge is lost primarily through leaching through the soil. But can it also be lost as runoff after surface application or with erosion? As the soil becomes saturated, nitrate can be lost through tile drainage flow. Within the nitrogen cycle, there are also transformations that are taking place, such as denitrification. And this is where the microorganisms convert the nitrate into nitrogen gas. And this will actually remove some of the nitrogen from the hydrologic cycle. Let's move to the phosphorus cycle. It's different from the nitrogen cycle because phosphorus is not converted into atmospheric gas, so it just remains in the system if it's not being utilized by crops, which is what has been referred to by some in recent publications as legacy phosphorus. This is because it can be re-released into the hydrologic system years after application. Majority of the phosphorus is lost as runoff and erosion, but inorganic or dissolved phosphorus can also be lost, just like nitrate, through leaching and tile drainage. Increased climate variability and frequency of extreme events are predicted over the next century. This will continue to influence the quantity and the quality of the water transported from our agricultural landscapes. Because of this, properly timing and placing the nutrients on the landscape is going to be critical for reducing runoff on leachate losses. Let's take a look at the graphs on the screen. The bars are broken up by decade. The graphs depict the relative number of extreme precipitation events per decade. Brown represents a drought condition, whereas the teal represents a flood condition. You can see in the western part of the United States, we start to see both drought and flood conditions varying per decade. Within the Midwest and the Northeast regions, we're seeing a tendency toward greater number of flooding events. Here is one additional figure illustrating this increase in extreme precipitation events. This figure summarizes the percentage of the precipitation falling during the top 1% of severe storms. So something to consider is that these high intense precipitation events often overload our conservation practices, because our conservation practices, our best management practices, are only designed to treat a certain quantity of water. And so as these intense rainstorms occur, the residence time moving through a system is going to be reduced, which means the efficiency to reduce the nutrients with those practices is going to be reduced as well. To overcome the challenges that result from excess precipitation, agricultural fields are often artificially drained by a network of subsurface pipes, tile drains, to remove excess water off the fields and allow for earlier spring planting. They're typically placed about 3 to 4 feet below the ground surface, and even though they're called tile drainage, they're typically constructed of corrugated tubing. But years ago, they were actually made out of clay tile, which is why they are referred to still today as tile drains. The construction of drainage ditches or installation of these tile lines resulted in an anthropogenic change to the landscape that affects nutrient loss. By design, tile drainage alters the natural hydrology. So we're trying to move the water off the field quicker. Artificial drainage networks, including those tile lines and drainage ditches, increases that hydrologic connectivity of agricultural landscapes as well. So that adds another pathway for nutrient loss. So what does that mean exactly? If you have an area of the field that in the past had been in a depression and there was never runoff taking place from that location, there was only infiltration. Now, with the tile drain in place, the water can infiltrate, make its way into the tile, and then that tile line directs it toward a drainage ditch, which is then connected to some stream or river. So what are the challenges? Our changing hydrology is obviously one of these challenges, but at the same time, there are compounding system challenges that must also be addressed. So I'm going to move through 6 of those challenges that were identified in this issue paper. Our current knowledge of nitrogen and phosphorus rates is imprecise. What does this mean? Well, crop nutrient needs can vary within and among fields as a function of soil physical, chemical, and biological properties, previous management activities, as well as year-to-year differences in the weather. Additionally, we have to think about the advancements in crop genetics and the large variety of crop hybrids. So that further complicates the nutrient recommendations. This is because differences may alter plant nutrient requirements and the efficiency of the plant at taking up nutrients from the soil. The imprecision of our agricultural systems also complicates the ability to collect a represented soil sample in the field. The development of new technology is needed to better inform and guide application rates in conjunction with research to better understand the impacts of nutrient placement and timing. This graph illustrates that fertilizer use efficiency has nearly doubled over the past 50 years, yet water quality still remains a concern. Even when farmers and crop advisors follow the best available nutrient recommendations, the applied nutrients may not be taken up by the crop that same season that they're applied. This results in less than 100% recovery. Our second challenge, nutrient reductions for both nutrient management and conservation practices are field specific. So for example, grass waterway or buffer strip may result in a greater nutrient loss reduction on one field where the runoff is more concentrated and less reduction effectiveness from a second similar field where there's a less slope and more diffuse runoff. This creates a large challenge for both conservation programs that are providing recommendations on practices and the farmers trying to decide which practice will fit best within their management system. Throughout the United States, there's this sense of urgency to solve water quality issues. This leads to a tendency toward applied research that focuses on quantifying practice effectiveness outcomes. Recognizing that some level of nutrient loss is unavoidable from even natural landscapes, one question that must be answered is what to consider as an acceptable level of nutrients and runoff in agricultural fields. A review of watershed analyses where edge of field water quality measurements were collected indicated that less than 5% of the applied nitrogen and phosphorus tends to be lost in runoff. Yet this small quantity can still result in environmentally significant impacts. Our third challenge, legacy nutrients may mask water quality impacts of current conservation efforts. Failure to decrease nutrient loads at the watershed scale may not imply that current conservation efforts are having no effect, and that's because of legacy nutrients. Those are the nutrients that have built up in the soils and groundwater over time, and they may mask or buffer the efforts of the current conservation practices. It's currently not possible to differentiate between recently applied nutrients and legacy nutrients. So for example, if there's a runoff event that takes place right after an application of nutrients and we collect a sample, well, we can't tell if the concentration that's measured in that sample is from that application that was just recently applied or if it was from nutrients stored up from an application maybe 15 years ago. And this makes it difficult to assess the effect of conservation practices as we move to larger scales. So moving from the edge of field to a watershed assessment. Additionally, it can take several years for most conservation practices to achieve maximum reduction potential. The presence of gullies, soil macropores, drainage ditches, and tile lines, they all serve as potential conduits for mobilizing nutrients and releasing this stored nutrient as a source. Some of the practices that were previously adopted in the late 1980s and early 1990s, so for example, like no-till systems across Lake Erie Basin, they've resulted in nutrient stratification, or in other words, higher concentrations of nutrients in the surface layers, specifically phosphorus, which have become an opportunity for losses through leachate and runoff as well. Our fourth challenge, most implemented conservation practices do not address dissolved nutrients. The practices were designed to trap sediment and the attached particulate form of the nutrient. The dissolved nutrients, these are the forms that are plant available. So therefore, as we lose these dissolved nutrients into our waterways, they can accelerate the rate of eutrophication. Our fifth challenge, few conservation practices provide in-stream nutrient removal. Focusing on just in-field and edge-of-field practices will likely result in unmet nutrient load reduction goals at the watershed scale due to the contribution from groundwater sources, stream bank erosion, and in-stream nutrient cycling. Lastly, conservation program success requires collaboration and cost-effective implementation. Current programs require farmers to voluntarily approach agencies to enroll in programs, and then once they're there, they have to choose which resource issue to address. Effective conservation programs reward local conservationists who build collaborative working relationships with landowners and managers who have the most critical environmental concerns for that region. Increasing program cost effectiveness through multiple approaches that engage industry organizations and companies and consider incentives for downstream ecological enhancement, those are needed to more effectively and efficiently decrease nutrient loss from agriculture. In summary, achieving agricultural water quality goals requires research to better understand complex processes controlling crop nutrient requirements and losses, the development of new conservation practices and technologies, and sustainable programs engaging industry and other regional stakeholders to prioritize goals and integrate complex attitudes and constraints associated with landowner conservation adoption. The complexities and difficulties associated with nutrient cycling and transport processes, management decision and practice trade-offs, and a program effectiveness highlight both significant progress that has been made as well as immense challenges to meeting both production demands and water quality goals. I'd like to thank you for participating in this webinar, and I hope that you have the opportunity to download and read the full issue paper. Thank you.